Hello everyone, my name is Vincent Kenville-Belair, and I'm the tech lead for TorchAudio, which is what I'm going to talk about today. The goal of TorchAudio is to provide building blocks to other researchers and engineers that allows them to bring research to production. This way, TorchAudio can accelerate the development of other libraries in the open source ecosystem. TorchAudio is built around the following core functionalities. The first functionality is I/O, to read and save tensors from various file formats like MP3, WAV, FLAC, and Sphere. We can also download and use common audio datasets where samples are loaded in parallel using Torch multiprocessing workers. The second functionality is transforms for audio and signal processing, such as spectrogram, MFCC, and resampling. The transforms are provided as neural network modules in TorchAudio.transforms. Since the transforms are written using pure PyTorch operations, the computations can be done on the GPU and they can be compiled using TorchScript. The third is SOX and Caldy compatibility. SOX and Caldy are audio processing library written in C++. For SOX, we provide an interface to use their transforms. For Caldy, we provide reading and writing of Caldy binary files, as well as equivalent features like spectrogram and NFBank. The final functionality is a distribution of models, along with canonical example pipelines for distributed training for major tasks. As I said, the first set of functionality revolves around I/O. Here's a small snippet using TorchAudio load and transform. The waveform variable is a tensor, which is read from file, and the corresponding sample rate of the file is read as a scalar. The TorchAudio transform spectrogram is given an input parameter to configure its behavior. It is then passed the input tensor, which computes a spectrogram tensor as output. What's special here that I want to highlight is that not only are the transforms tethered to TorchNN module, and so can be compiled using JIT, but the load function uses torch bindings, and so can also be compiled and ported wherever JIT is supported. The goal is thus to make it possible to JIT an entire pipeline to be run in production easily. We support several datasets for different tasks, for instance LibreSpeech for speech recognition, LibreTTS for text-to-speech. The next set of functionalities I mentioned is transforms. As I said before, they're written in pure PyTorch, and as such support batching, TorchScript, and GPU. Here's another example. Since each transform is a TorchNN module, they can be combined in a standard sequential wrapper for convenient data augmentation. Here, we take a spectrogram, apply a random time stretch, compute the complex norm, apply a random frequency masking and a random time masking, and then convert the amplitude to decibel. Frequency masking and time masking are part of SpecAugment, which is what I'm illustrating in the image. A band of frequency and another in time are randomly masked. The code is divided in functionals that perform the computation, and a transform, which is an NN module that wraps each functional and keeps their state. Here I'm listing a few new functionals that we added recently. You can see, for instance, mask along axis that is used within the frequency and time masking. We also have several biquad filters that are used in signal processing, or a voice activity detection operation to detect voice. The next functionality is the interface with SOX and Caldy. For SOX, we offer a way of using their efficient C++ operations directly within PyTorch in a torch-scriptable manner. For instance, here I'm applying a sequence of gain, speed, rate change, pad, and trim using applyFX tensor directly on the PyTorch tensor. For Caldy, TorchAudio provides a wrapper for TorchAudio transforms that mimics the flags provided to Caldy binaries. You can also read ARC and SCP files through TorchAudio so that the processed output of Caldy can be used within your TorchAudio program. Caldy is used quite a lot in the audio community, so we want to make it easy to interface with it. The final set of functionalities that I wanted to talk about is the addition of models within the library. For speech recognition, we added a training example pipeline for speech recognition that uses LibreSpeech dataset and the wave-to-letter model. For text-to-speech, we added a vocoder based on the WaveRNN model, along with an example training pipeline in the example folder that uses LibreTTS dataset. For source separation, we added the conv-tas-net model and an example training pipeline with the Wall Street Journal Zero mixed dataset. Before finishing, I would like to highlight a few features that are on our roadmap. First, we would like to include the call to pitch feature extraction due to demand from the community. Second, we are interested in including a beam search decoder interface. This is especially useful for speech recognition application. And finally, another loss that has been requested by users is the addition of the RNN transducer loss. To use and learn about PyTorch, you can visit pytorch.org/audio. It contains documentation about the API, installation instructions, tutorials, and links to the GitHub page. We also have a new tutorial for the recognition of speech command. Have fun playing with it. TorchAudio is compatible with Linux, macOS, Windows, and supports Python 3.6 and up, just like PyTorch. Thank you for watching.